So in this session we are going to look at a different take of event handling programs, a functional view of events that's embodied in functional reactive programming. You've seen that reactive programming is all about reacting to some sequences of events that happen in time. The functional view is that we can actually take such a sequence of events and aggregate it into a signal. So a signal is a value that changes over time, and it's represented as a function from the time domain to the value domain. That means that instead of propagating updates to immutable state one by one, we define new signals in terms of existing ones. In a single operation, we can define a new signal in terms of signals that we have already defined. So let's make this concrete with an example. Let's say we want to track mouse positions, or here we'll substitute the mouse with my pen. When the user moves the mouse, usually a sequence of events is fired. Each time the mouse is at a new position, the application gets a mouse moved event with the current position of the mouse. And it would have to handle that event by updating its internal state, and all these updates would typically be imperative. How can I lift this into a functional viewpoint? So the core idea is that I define a signal, call it also mouse position, which is now a signal of position, which at any point in time represents the current mouse position. So it's a function from the domain of time values to this curve. At the initial time value, the position was here, and then it would go progressively until at the final time value, the position was here. That gives me a function from time values to positions. Functional reactive programming started in 1997 with the paper Functional Reactive Animation by Conal Elliott and Paul Hudak, and Conal also wrote a language called Fran, which was implemented as an embedded library in Haskell. There have been quite a few FRP systems since, both standalone languages and embedded libraries. The list is too long to give you a complete picture, so I just give you some examples. Flapjacks is one. Elm, Bacon.js, both target JavaScript. React4j is a Java library that does a minimal reactive programming framework. Related but not quite the same are the event streaming data flow programming systems such as Rx. In fact, we will see Rx more in 2 weeks. They are related to FRP, but commonly the FRP in the strict sense is not used for these. We'll introduce FRP not with one of the existing frameworks, but with a really minimal class, which we will define ourselves, which we call FRP.signal. And we'll explain the implementation of FRP.signal at the end of the next module. FRP.signal is modeled after the library Scala React, which is described in the paper Deprecating the Observer Pattern by Ingo Meyer and myself. And in fact, the React4j library is also influenced by this Scala React library, so it has abstractions that are a bit similar to what we are going to see here. So let's have a closer look at signals. There are two fundamental operations over signal. First, I can obtain the value of a signal at the current time. In our FRP signal library, that's expressed by applying the signal to an empty parameter list. So mouse position, open parents, close parents would give us the mouse position at the current time. The second fundamental operation is to define a signal in terms of other signals. In our library, that's expressed by the signal constructor. So let's do an example. Let's say I have drawn my curve, and I have given a rectangle like this, and I want to define a new signal which is either true or false depending on whether the curve or the mouse was in the rectangle or not. So that new signal would look something like this, would start with false, and then at this point in time it would jump to true, and it would stay true for a while and would go back to false. So that's false, and that's true. So it's a discrete signal with two states. Here's how I would define it. I would define the signal in rectangle, which takes as parameters the coordinates of the rectangle given as a lower left corner and an upper right corner. And it's defined by this expression here. So what that says is that at each point in time, I return the signal that looks at the mouse position at the same point in time, at the current point in time, and returns whether that position is between the lower left and the upper right corners. So we've seen the signal syntax to define the rectangle signal in terms of the mouse position signal, but it can also be used to define a signal that has no dependencies and always defines the same value. So for instance, signal 3 would define the signal that was constant 3. That was always the number 3. So we've seen constant signals, but how do we define a signal that varies in time? Well, we've seen already some of these varying signals are defined externally, something like mouse position that the system could give us. We can also map over the externally defined signals that vary in time, and that gives us new signals that vary in time. Or the other way is that we can use a var. A var is a subclass of signal that we are going to see next. So far, all values of type signal are immutable. A signal is an immutable function from time to the signal values. But in fact, our library also defines a subclass var of signals for signals that can be changed. The change is done by means of an update operation which var provides. And that update operation allows to redefine the value of a var signal from the current time on. So if we look at this example here, we define sig to be a var 3, so that it's a signal that for now is always the constant 3, until the point where I define an update operation on that signal. From that point on, it will always be 5, until, of course, there's the next update operation maybe happening in the future. So the update operation uses the name update for a reason, because in fact in Scala update calls can be rewritten as assignments using some syntactic sugar. You've probably seen that already when working with arrays. For an array R, you would write R of I equals 0, and what actually happens here is that this expression, that this assignment is translated to array.update I and 0. And that would call the update method in class array, which has this definition here. So update takes an index and a value of the element type of the array and returns unit. So under the covers, when you write an indexed assignment like that, you really get a call to update. Generally, an indexed assignment like f of e1 to en equals e is translated by the Scala compiler to f.update e1 en e. And that works not just for arrays, but for all types that define an update method of the right arity. And that also works if n equals 0, so if there are no indices, that means that the call f open parens close parens equals e is a shorthand for f.update e. So since we have such an update method on signal, it means that sig.update 5, a call like that, can be abbreviated to simply sig open parens close parens equals 5. You probably noticed that signals of type var look a bit like mutable variables, where sig open parens close parens is dereferencing, reading the variable, and sig open parens close parens equals new value is writing the variable, or update. But there's a crucial difference. We can map over signals, which gives us a relation between two signals that's maintained automatically at all future points in time. Whereas for variables, no such mechanisms exist. We have to update all variables manually whenever some dependent variable changes. So for instance, if we have a variable a initialized to 2, and then b would be 2 times a, and then we would update a equals a plus 1, then the value of b does not automatically get updated together with the value of a. So b would still be 4 even after that assignment. We'd have to update it manually to say, well, b is now again 2 times a, so that would give it 6. Whereas if we did the same thing with signals, then it would look like this. So we would have a signal a, which is assumed to be a var signal, constant 2. The signal b is assumed to be 2 times a, and that assignment would establish already essentially the relationship between b and a forever in the future. So if now a is defined to be 3, then the signal b would be automatically updated to 6. We're going to repeat now the bank account example we've seen in the last section with signals. We will add a signal called balance to bank accounts, and we will define a function consolidated which produces the sum of all balances of a given list of accounts. So I have on screen my class bank account from essentially the original example without any event handling, deposit and withdraw method, and this variable balance. How do we make this into a source of an FRP signal? Well, one approach would be to say, well, let's make balance a signal. So it would be a val, and that would be a var of 0. So balance is still a variable, but now it's a signal. So now we say, well, the deposit method would update that signal. Let's just write it like this for now. And the amount method would test that signal. And the withdraw method would test the signal. And again, update it like this. So that's our strawman for a bank account with signals. That was easy, right? We just changed the var balance into a variable signal and brought everything over. So let's test that with a worksheet. I have written a worksheet accounts, and I've given already the header of a function consolidated, which should return the sum of all the balances of the accounts in this list here. So the type of consolidated would be then a signal of int. And its definition would be, we define a signal, and the signal is defined by means of mapping over all our accounts. For each ones we take the balance, and we take the sum of the whole thing. And of course we have to take the balance at the current time, so it would be written like this. So that gives us the function consolidated. What we do now is we define, as before, a number of bank accounts. And we want to find out the total balance in consolidated, so the value of consolidated at the current time. All right, so we get 0 as expected. Let's deposit some amount in A and try again. Oops, we got an assertion error. So what does it read here? It says cyclic, let me just bring that up, cyclic definition, cyclic signal definition, that's what it says. So what have we done wrong? So it must be in the bank account. Let's bring that bank account up again. So in fact the error appeared at this line here, and if you look at this line, then you must conclude that indeed it makes no sense whatsoever. What we've done here is to say, well, the signal balance, which is a function over time, is the same as itself plus amount, where amount is greater than 0. So obviously an equation like that has no solution. You can't define a function that at each point in time is the value of the function itself plus amount. So that didn't work, and in fact the system has caught us out by throwing an assertion which says there was a cyclic signal definition. We have defined balance in terms of itself. So how do we fix it? Well, what we need to do to fix it is we have to pull out the balance signal into a separate definition here that pulls out the current value of balance and then just does this thing here. And we do the same thing here. So while B equals balance, and balance equals B plus amount. So how is that different? Well, what we do now is to say we take the current value of balance, call it B, and then define the new balance after that to be that value plus amount. So what we do now is not define a cyclic definition, not have a cyclic definition, but indeed define a constant function which will return at all points in future the value of this expression here. So you see that the interaction of state and functions is very subtle, as we have observed at several points before. It makes an obvious difference whether balance here is defined as the right-hand side of a signal definition or pulled out into its own val. Let's redo the worksheet with that example. And in fact, now we get the correct result. The A deposit is 20. Let's deposit as before 30 in B. Call it again. And that would give us this here. Let's go a little bit further and say we want to have another signal which defines an exchange rate. Let's call. Let's say the exchange rate is first 246, let's say, dollars for bitcoins. And let's say our value, our total sum is in dollars is then what we had before, the signal that takes C times the signal exchange rate. And now we would have a different signal in dollar which has this value here. Now if we change, let's say B again, B withdraw 10, and look at the result in dollar, then you see that the deduction in B is reflected in our in dollar result. So first the signal C got updated, and then the signal in dollar got updated as well. So that was the bank account example redone with signals instead of subscribers. If you compare the two solutions, then you will notice that the solution with signals is much shorter, and you could also argue much cleaner because there's much less state updates than in the observer solution, which is inherently imperative. We've also seen in the example that there's an important difference between a variable assignment, such as this one here, and a signal update, such that the one that you see here. In the first case, that in that variable assignment, the new value of v is the old value of v plus 1. So implicitly, there's a notion of old value versus new values. When you update a signal, there's no such notion. So what you are trying to say here is that, in effect, that the signal S is the same as the signal S plus 1, which obviously makes no sense. So here's an exercise for you. Consider those two code fragments. The first one says num equals var1, and we have a signal that is num times 2, and then we update num to be 2. And the second one is quite similar, so we start with a var num equals var1. The signal twice is as before, but finally we define num to be equal var2. Are those two code fragments equivalent? That means would they yield the same final value for twice? So if I evaluate twice here and I evaluate twice here, would I get the same value? Yes or no? So let's visualize how these two code fragments behave. In the first case, I have the num signal, which is constant 1, and the twice signal, which is constant 2. Then at some point I change num to 2, and twice will consequently jump to 4. So that's the update of the first code fragment. Let's have a look at the second one. So again, I have num equals var1, and twice is 2. But what I do now is I define a new signal num and assign it to the variable. So after this point here, num in fact points to a new signal that is has the value 2. whereas the twice signal in fact would still depend on this signal here that I have created up here, so it would stay 2 forever. So while I have here 2 as the final value, in the first code fragment it was 4, and the 2 fragments are indeed different. It just shows a little bit the subtlety that you have with signal update versus variables. It gives you another aspect of that same difference.